Hello everyone, my name is Honghe Zhou. I'm from Towson University. The topic of our research is reconstructing Android user behavior through time-stamped state models. On July 12, 2014, a boy named Connor Roy committed suicide at the age of 18. His girlfriend, 17-year-old Michelle Carter, was convicted of involuntary manslaughter in Roy's death. A key piece of evidence that led the judge to make this ruling was the numerous text messages that Carter sent to Roy before his death, urging him to commit suicide. This case is commonly known as the text message suicide case. In this case, the information in the mobile devices has played a key role in the crime investigation. According to statisticians' prediction, the number of worldwide mobile device users is expected to exceed 7.49 billion in 2025. With the popularity of mobile devices, a lot of user information is transmitted or stored on mobile devices. User operations are one of the most important pieces of evidence. They can tell what a suspect or victim was doing with their mobile devices. However, there is a lack of effective techniques that are capable of helping forensics investigators extract user operations from Android mobile devices and reconstruct user operation state models with timestamps. Therefore, how to extract user operations and reconstruct a criminal or victim's user operation model at a time of interest with mobile devices. Our research aims to solve this problem. In this paper, we propose an approach that automatically identifies user operations from Android mobile device event logs and constructs a time-stamped state model. And then, let me introduce some important concepts used in our approach. First is lifecycle pattern. A lifecycle pattern is a sequential combination of Android lifecycle callbacks recorded in event-related logs when the user conducts operations on the phone. This figure shows the Android lifecycle inside one activity. From this figure, we can see some lifecycle pattern and their corresponding user operations. For example, when the user clicks the icon of an app, the callbacks are sequentially executed in such order: on create, on start, and on resume. So this is the lifecycle pattern corresponding to the user operation click app icon. Similarly, if the user click power button idle for a period of time or return to home screen, the callback sequence will be on pause and on stop. When the user click the power button from sleep mode to turn on the screen, or click application icon from home screen to relaunch the app with the app running in the background, the callback sequence will be on restart, on start, and on resume. Once the user quits the app, the callback on this tree will be coded. And this figure shows the life cycle between two activities. When the user clicks a green widget within an activity, the phone will jump from current running activities interface to another activities interface. At this time, if another activity not in the background, the callbacks were executed in such order: on pause of activity 1, on create, on start, on resume of activity 2, and on stop of activity 1. If another activity in the background, the callback sequence will be on pause of activity 1, on create, on start, on resume of activity 2, and then on stop of activity 1. The second concept is user operations. In our approach, we define user operations are actions that the user performs on an Android mobile device. Note that only those user operations that cause a transition among Android activities are considered in this research, because Android event-related logs only record when an activity state is changed. As we mentioned above, these operations include click application icon, click power button, idle for a period of time, return to home screen, create an application, and click Agree widget within an activity. And here are some examples of our target user operations in the research. First is operation click power button. If users click the power button, they can turn on or turn off the screen. We use log tags in the Android system logs to distinguish these actions. The second example is click Agree widget within an activity. In this example, we enter in the background interface and switch from one app to another. This activity jump process will be detected by our approach. The third concept we defined in our research is time-stamped user operation state model. A time-stamped user operation state model is a comprehensive graph-based model that captures a series of user operations, target grid widgets, and every operation's timestamp. In other words, a time-stamped user operation state model includes the sequence of action a user takes when interacting with the phone to achieve a goal or complete a task. This figure shows a time-stamped user operation state model of ColorNote app generated by our approach. ColorNote is a simple notepad application. In the state model, each node represents an activity, and each edge is a transition annotated with user operation and timestamp. The basis of this approach we proposed is to identify user operations from corresponding log patterns that are triggered by these operations. This approach includes three phases: log file acquisition and processing, log patterns discovery, and time-stamped user operation state model generation. First, we obtain Android event-related logs that record the information about the Android activity lifecycle. After obtaining raw logs from the event buffer, we filter the logs using tags to collect logs related to the Android activity lifecycle. Different user operations trigger these callback functions, related logs in different sequences and patterns. Therefore, in the next step, we investigate the relationship between user operations and event-related log patterns. Based on this information, after the user operates the phone, we can analyze a sequence of lifecycle. Now, we need to analyze this sequence to get the sequence of user operations. This process is called lifecycle sequence segmentation. In the algorithm, we store the text of logs in a string called log tag, and put all the keywords in an array called dict. Each keyword represents one lifecycle pattern. The array dict acts as a dictionary for the algorithm. Then we use the mixed-meal matching method to separate the string log tag. We begin with the first character of the given string log tag and search for the longest word in the dict starting with this character. After we find the matching word, we store the result in the operation array and continue the search in the string log tag. After the search is finished, the result represents a sequence of user operations analyzed from the logs. Using user operation sequences, we implement a program that can automatically generate time-stamped user operation state models. Within this state model, each Android activity involved in the user operations becomes a node, and each transition becomes an edge. To evaluate our approach, we conduct an experimental evaluation using real-world Android applications to answer the following two research questions. First, can we generate time-stamped user operation state models from Android logs and demonstrate how the mobile device was used during a time of interest to assist in digital forensics investigations. Second, to what accuracy can timestamp user operation state models generated by our approach achieve with real-world Android applications? And this is our experimental environment and subject. We conduct the experiment using a Google Pixel 7 Pro with Android 13. To randomly and intelligently simulate user operations, we use Drawbot, an Android text input generator, in this experiment. We select 5 categories of Android applications from Google Play Store to evaluate the effectiveness of our approach, including note-taking, shopping list, weather forecast, to-do list, and expense related. These are the steps of our experiment, including using Drawbot to simulate user operations, generating timestamped user operation state models, and verifying the coverages of timestamped user operation state models with Drawbot's action records. This figure illustrates the detailed experiment process. First, we use Drawbot to simulate the user using the Android mobile device for 1 hour. Second, after Drawbot simulates and records user operations, our tool extracts and filters log files of these operations from the mobile device. After we input the time period of user operations and the package name of the target application into our tool, the tool extracts event-related logs of the app corresponding to the given time period. Then, the tool uses these logs to generate a time-stamped user operation state model. Third, we compare time-stamped user operation state models generated by our approach to Drawbot action records to evaluate the effectiveness and accuracy. We only consider operations that cause a transition among Android activities in this research. To evaluate the effectiveness and accuracy of our approach, we use 3 metrics to assess the effectiveness and accuracy of our approach in our research: Android activity coverage, user operation coverage, and state model coverage. Android activity coverage aims to compare the Android activities detected by the proposed approach to the activities recorded by Drawbot. User operation coverage aims to compare the user operations detected by the proposed approach to the actions recorded by Drawbot. And the last, state model coverage aims to compare transitions in state models detected by the proposed approach to the state recorded by Drawbot. In other words, it shows the coverage of the user operation sequence. And here is an example of evaluation results using Experiential as an experiment target. Experiential is an open source application published by Google and is commonly used for automated Android UI testing. The picture on the left shows the time-stamped user operation state model of using Experiential. For activity coverage, it shows that there are 3 activities detected during the experiment: Nexus Launcher activity, My activity, and Show Text activity. And from Drawbot action record, shown as table on the right, the actual Android activities invoked by the user's operation are also Nexus Launcher activity, My activity, and Show Text activity, which are the same as the activities detected by our approach. This means that all 3 activities are detected by our approach Therefore, the Android activity coverage for this app is 100%. For user operations coverage, the picture shows 4 user operations are detected. Click App icon, click Open Activity and Change Text button, click Return button, and click Home button. And in the Dropbox action records from corresponding Android activities, we can analyze that from Nexus launcher activity to My activity represents user operations, click App icon. From My activity to Show Text activity represents user operations, click Open Activity and Change Text button. From Show Text activity to My activity represents user operation, click Return button. And from My activity to Nexus launcher activity represents user operation, click Home button. And we can find that the user operations in Dropbox action records are the same as the 4 user operations detected by our method. This means that all 4 user operations are detected by the model. Therefore, the user operation coverage for this application is 100%. For state model coverage, we want to compare the transitions of user operations detected by our approach and transitions of user operations in the Dropbox action records. This part of the experiment takes into account the user operations sequence and the time of user operations. Since the transitions of actual user operation sequence are the same as the transition set recorded in the Dropbox action record, the state model coverage is also 100%. This table shows the result of the experiment for the 10 apps. From the result, we can find that our approach achieves a mean of 100% activity coverage, a mean of 94.3% operation coverage, and a mean of 95.5% state model coverage. In other words, a mean of 94.3% user operations and all activities involved in these user operations can be reconstructed through our approach using Android logs. In addition, our approach can accurately identify the sequences of nearly all user operations along with their activities with timestamps. The standard deviation of operation coverage reaches 0.052, and the standard deviation of state model coverage reaches 0.028. They indicate that the results of our approach are stable. In this paper, we incorporate timestamps into traditional state models, which enables investigators to identify user behavior with corresponding timestamps. We identify a set of patterns and mapping relationships between different user behavior and Android logs. We propose an approach that can automatically extract event-related logs and reconstruct time-stamped user operation state models that include all user behavior on the phone without rooting the phone. And based on experimental evaluation, we have demonstrated the feasibility, effectiveness, and accuracy of this approach to capture user operations and reconstruct a criminal or victim's behavior through the analysis of the user's Android mobile device. For future work, we would like to expand our approach to other mobile platforms, such as iOS. We also plan to formalize user operations and evidence and facilitate the digital forensics analysis process. This work is supported in part by the United States Department of Justice. Thank you for listening. If you have any question, please feel free to contact me. Here is my email address. And welcome to our project website. Our project is called Cyber Forensics for All. We aim to construct and share digital forensics educational resources. Here are our links. If you are interested, please visit our website and contact us. That's all for my presentation. Thank you.